Hi guys, welcome. This is module CM3292 and this is the mini e-lecture on inductively coupled plasma spectrometry. That's experiment 2A. So the structure of this lecture is on the page in front of you. I will pause for a moment on the references. The Skoog et al. Good solid analytical chemistry book, and I heartily recommend it. If you're more interested in atomic spectroscopy per se, I recommend the Robinson reference. It's actually reasonably written, probably not quite as smooth as Skoog, but it will give you detail on ICP and the other emission and absorption atomic spectrometry techniques. So very much recommend it. Okay, we'll move on. As for all of these lectures, I need to underline what the aim of the lecture actually is. What we're doing here is we are briefing you on the underlying theory of the equipment that you're using and occasionally the techniques you're using. So in this lecture we could talk about just atomic spectroscopy, but you're particularly using ICP-OES, so that's what we're going to concentrate on. It's not, however, to brief you up on how to use the equipment. If you think of the materials you have for this module, you've already got a video showing you how to turn the equipment on, to do an analysis, get the data off, and sleep it or close it down. So this is not about that. It's also not about what you're doing in the laboratory, because you have the practical script. So again, I suppose it just clarifies what this is about. It's solely about the underlying theory of the technique you're using. Some of the stuff that we talk about here you'll have met before, probably not packaged as an analytical technique, but in terms of the basic phenomena, and in which case I'm going to touch on some of that, but if you want more detail, go back to your previous notes, probably in spectroscopy or physical chemistry. This practical, 2A rather than 1A that the slide says, comprises of 3 mini lectures. There's polarography, there's sampling, and there's this one, which is inductively coupled plasma spectrometry, or ICP-OES. Okay. So, this is a summary description of the method, which we'll come back to again at the end. It's probably will mean more after this lecture. Right, so where have you heard of atomic spectroscopy before? Probably from the world of physics or physical chemistry or chemical physics, where we look at maybe distant galaxies or distant stars and want to establish what elements are there. This cartoon you can look at yourself. Effectively, we're using light from a particular galaxy or star, and we're analysing it spectroscopically. The little spectrum on the right, that's the type of result you get from these analyses, and each of those spectra is characteristic, and hence we can establish what elements and in what form they are in these distant systems. Okay, so that's really just where you might have heard of it before. Let's now bring ourselves to CM3292 and the method you're going to be using. The ICP, which is what I'll call it from now on, actually has really only two instrumental components, plus the data handling and stuff like that. The first component is the ICP itself, and that comprises, in the yellow box that you can see here, that comprises of the sample and the sample introduction technology, the nebulizer, the torch, and the transfer optics. The second part of this equipment is the spectrometer with its detector. The rest of this kit is simply the data handling and the electronics. So, how does it work? What's happening? What I'd like to do is think of maybe some of the techniques that you may have met before. So, atomic absorption spectroscopy, which is not what we're doing, actually measures the absorption of light by free atoms. So usually it's in an acetylene flame, and you spray, rather in the same way with ICP, you nebulize your sample so it goes into the flame as a fine spray. You're shining light of a specific wavelength, that is a wavelength that can be absorbed by electrons in the metal ions that are in the spray, your sample that you're spraying into the flame, and these absorb that light as photons at a specific frequency or specific wavelength to give you some excited state. And with atomic absorption, you are measuring that absorption. By definition, atomic absorption, atoms absorbing. Okay, so that's plum and dandy. Emission spectroscopy, though, is something different. In the plasma, every metal ion from the sample is immediately excited. It's being collided by argon, 7,000 Kelvin, and effectively every metal ion you find is going to be excited, and the electrons, the excited electrons, the promoted electrons drop back down, sometimes to the ground state, but more often to a state, maybe a vibrationally excited level in the ground state. As the electrons fall from the excited state to the ground state, they emit radiation with a characteristic frequency. You might recall Planck's law, E equals h nu. And it's that light which is measured, and that light which forms the basis of the concentration measurement of any metal. Because these metal atoms are effectively all excited all the time, you're just measuring the emission, not the absorption. Where did flame photometry, where did ICP come from? Well, probably the earliest emission technique that you've used is good old flame photometry. Effectively, you're in a flame at maybe 2000 Kelvin, so it's quite low energy. It's effectively a very low energy atomic emission spectrometer, and at that energy, probably only group 1 and 2 metals, probably the only ones that you can usefully detect. And that ties up with, if you remember practicals, you were looking at sodium or potassium, maybe occasionally calcium. Okay, so let's look in detail then at the first part of the ICP, the sample, the torch, and the transfer optics. Now, the torch, so-called, is typically a set of concentric quartz tubes usually, and through these tubes you have a flow of argon gas. Around the tube is effectively a very large or very powerful RF generator, which gives you an intense magnetic field. All you then need to do is spark the argon, just a little, like a thing you light your gas cooker with, and the argon will ignite to form a plasma. Now that effectively you form Ar plus ions, and those from that original spark, those A plus ions, which are very excited, moving very fast, they collide with other argon atoms, and so the flame, it's not a flame, it looks like a flame, but the plasma is then continued via these inelastic collisions. The magnetic field focuses these charged particles, and so that gives you the background matrix in which you're going to do your analysis. I've called it a plasma flame purely because it looks like a flame, as you'll see in a moment, but actually this is much hotter than any flame that you're going to get. So then we have our nebulizer. So we introduce our sample as a solution usually into the plasma, and there it's immediately the metal atoms are collided with by the very excited, fast-moving argon plus ions, which effectively passes on enough energy to excite the ground state electrons of the metal into an excited state, and then all that happens is that the excited state decays, the electron drops back to a ground state, not necessarily the lowest vibrational state of the ground state, not the lowest vibrational level of the ground state, and emits a characteristic radiation as it does so. Now, clearly, those wavelengths are characteristic of the element. There are a number of different excited state destinations for your ground state electrons. Therefore, you have a number of lines in your atomic spectra. Staying with the torch for a moment, this is the ICP torch, and or a picture of, and you can see why it's tempting to call it a flame. So the argon is coming from the left of the picture, and the very white area is the center of the plasma, and as the argon flows from here through out there, so it's cooling, and of course it does look like a flame, but your metal ions are being introduced here as well, so effectively you then have the plasma matrix where you can measure the light emitted from your metal ions. So on this slide we see a schematic diagram of the torch we were just talking about here, with its radio frequency power supply and the flame-like shape of the plasma, and you can see that the sample, which is an aqueous solution of the salt, is pumped at a constant rate into a nebulizer, and a portion of that sample is then introduced into the heart of the plasma. So the metal ions, the excited metal ions, relax as they emit energy, as the electrons drop back down to ground state, and therefore they emit light. That light is transported then very much as the solar physics diagram to a diffraction grating and a prism, and we have a solid state CCD detector which measures the wavelength and measures the intensity of that light. The optics I'm not going to talk too much about. Effectively their entire role is simply to transport the light from the plasma into the spectrometer. Okay, we've just talked about the spectrometer. At root it's fairly simple. Effectively it simply, as any spectrometer, splits light into its component wavelengths and then measures those wavelengths and the intensity of those wavelengths. So this is sort of stuff you've known since O-level or A-level. You're aware that electrons fill in a order determined by energy. Always the lowest energy configurations are filled first. So if we build up the element iron, we need a number of electrons for iron. So we start building our electrons. The lowest energy place to put them is the 1s orbital. So we put 2 in there. We need to add more electrons. It's 2s. So we've got 4 electrons. Add another 6 electrons. So we've got 10 electrons in the 2p. Then we start adding electrons to 3s. So we've got 12 electrons, 18 electrons, 20 electrons when we get to 4s. And the next lowest energy level is not 4p but 3d, and the d orbital, as you know, can hold 10 electrons, so we get to 26 electrons. Now in that d orbital, we effectively, our 6 electrons, 2 of them are spin paired. That is, they have opposite quantum numbers, spin quantum numbers, and the remaining 4 electrons are unpaired, because this is the most stable configuration for those electrons in that d orbital. So we introduce our iron atoms into the plasma, and they are instantly excited, and then they relax, and in that relaxing, as we just talked about, they emit characteristic frequencies. And so this diagram here on the right is the line spectra for iron. It's not 1 or 2 lines, because you have a number of electrons in the ground state that at 7000 Kelvin can be promoted to excited states and then relax. And of course each element has its own characteristic spectrum, in the same way that iron has its characteristic spectrum. Okay, it's probably worth just reviewing the advantages of ICP over previous. So it's much hotter. The plasma is much hotter than any flame. Probably the highest temperature flame you like to get is maybe 3000 Kelvin. Electrical discharge maybe 4000 Kelvin. So this is considerably hotter. It's capable of exciting all metals and metalloids in the periodic table, so it's actually applicable across a wide range. It's much more stable than a flame, and the background is much lower because it suffers from fewer interferences. As long as sample is fed continuously into the plasma and argon is supplied continuously, the plasma is sustainable and the system is stable. Right, There are a couple of particular interferences. Arsenic, antimony and bismuth, for instance, there are difficulties using ICP for those. But largely, the summary is probably fairly straightforward. Using modern computers, one can program in the spectra of particular elements and therefore establish what you have. I think probably I've said enough, so I will go. Good luck and enjoy the practical.